This is a third lecture on simulation, and I'm going to continue in the same direction. Last time I talked a good deal about why should you believe it's relevant. Now I'm going to show you much more closely how it is that you get good or bad answers. There's a classic expression, garbage in, garbage out, the garbage meaning bad values. Well, I'm going to show you it is not true. From garbage in, I can sometimes get good answers out. From good answers in, sometimes I can only get garbage out. It's saying isn't true, although it is very appealing, and I need to show you in detail how this can happen. Now, since most of the simulations of the type I'm interested in involve differential equations, I will look at a simple first-order differential equation. In the xy plane, you give me a point xy, I know the slope. Every point on a plane has a slope. I could draw them one by one, but it's much easier in particular cases to do something a little different. For example, y prime equals x squared plus y squared. When x squared plus y squared is 1, the slope is 1. All along this, I have a slope 1. If I have a smaller circle, I have a lower slope. And of course, the origin, I have a 0 slope. And further on out, I have steeper slopes. And you can see the solution consists of, say we start the origin and come up like this. It consists of going so that each point you are following the local slope. Now, this is a very powerful method. I'm putting it on the board for several reasons. I told you I used to eat with the physics department in the restaurant. Well, every once in a while somebody would say something and I would say, if I understand you correctly, this is the differential equation you're talking about. And we would argue about differential equation. And if it were first order on one of the placemats, I'd make a quick sketch like this and say, well, all the solutions go off to infinity or something. Well, it can't be. My remark was, you've given me the differential equation wrong, or you misunderstand what the phenomenon is. Which do you want? And they would go after it and they finally decide where the error was. Now that's a trivial exercise. Anybody can do it, but almost nobody did. I use direction fields to help them in the very early stages of thinking about something, get misconceptions straightened out. So I put a high value on simple direction field calculations. A simple sketch will often reveal an enormous amount about what is going on. Now, since this is bound to be graphically inaccurate, you say, well, what you want to do is, starting at some place, calculate the slope. Let's say, suppose there's a true solution like that. Go here, calculate the slope. Go there, calculate the slope. But you see, I'm always using a slope that was. I'm not really on the curve. And I'm going to lag further and further away from it if I do this. So the next idea is a little bit better. Let me start here at my starting point, x0, y0. Go along this line to get a new point, a distance delta x. Calculate the slope there. And from these two slopes, average. Use the average slope of the two, which is a little bit higher, and predict that point. So I predict the point. Using the slope there, I make a new correction. I calculate a corrected point. If the predicted and corrected points are close, I must be accurate. If they're far apart, I'm taking too big a step delta x. And this way, I can get a much more accurate answer because I'm using some information about where I'm going to be as I make the final step. That's known as Euler's method. It's not a bad method. It's fairly simple. The predictor and corrector. Now, if the predictor and corrector are far apart, evidently I have to cut the step size, and traditionally you cut in half. If they're very close, I should double the step size. So the predictor corrector, by comparing the size of the predictor with the corrector and using a little bit of theory, you can tell whether you want to increase or decrease the step size. So you can do something near optimal calculations. You aren't wasting a lot of time when you don't need to. For example, in getting to the moon, in mid-flight, the thing is coasting in quite a smooth gravitational field, a combination of the sun, the earth, and the moon. And it's a very, very smooth trajectory there, and you can take step sizes of an hour at a time practically and not make much mistake. But when you're near the earth or near the moon, you've got to take small step sizes, because then a small motion affects significantly the amount of gravity you're going to feel. So the step size starts out very fine, opens up to very large step sizes, and comes back down to small step sizes as you're coming in on the moon. That's characteristic of many problems. You don't use the same step size all the way along. Well, now, this was effectively using straight lines, or if you really want to be fancy, I might claim they were quadratics. It is customary in numerical analysis courses to use a polynomial to predict. In other words, use several old values and their slopes to predict where the point will be. Having gotten that slope, using old values and old slopes and the new slope, calculate the new point. And if the predictor and corrector are close, fine. If they're not, you're out. And the typical one is fifth order. The error term depends on the fifth derivative. It's correct for 1, x squared, x cubed, x fourth. And that includes the Gaddis-Bashford method, Milne's method, Hamming's method, and various other methods of doing differential equations. They all work at about the same amount. Not that some of them don't. If I am doing orbits of the planets, which have very weak interaction, I may very well go to methods which are highest 10th order. But typically, we work at about 5th order. And it's about what works out most of the time. Once in a while, you drop back to Euler, but the 5th degree one is much better on the average. And we get somewhere along the way on that. Now, I want to take another difference equation and look at the thing more closely. If y is equal to a e to the minus x squared, y prime is minus 2xy. Now, this direction field, knowing what y as an x is, and the exponential comes down very rapidly, much more than that goes up, you find you have various slopes here, and but at x equals 0, they're all horizontal. And then when y changes sign, they come down the other way. And so you see 2 points. One point comes up like that, we'll go back and back down. Another one nearby. Yeah, let's get this thing. And another one nearby. You see the close points here produce very large errors there. It's the nature of the problem. So if I have a very good numbers here, I do not have, for this differential equation, good answers here. On the other hand, if I start here with bad numbers, I come out with a very good answer over here. You see why? Good answers in, garbage out. Garbage in, good answers out. From here to here, I can get from here to here accurately. What I can't do is get from here to here. Now, you have put in your mind there little tubes about those solutions for the error. That's fine for first order. When you try to picture a thing in 28 variables, as I talked about the Navy intercept problem, then those tubes you're drawing are not what you think. You remember back when I discussed in lecture 9 the n-dimensional space and the 4-circle problem? Remember, even by 10 dimensions, that inner circle got outside the square? Remember? In 28 dimensions, these tubes that you're likely to picture are not quite what you wish they were. There's the reason why I put it on a 4-circle problem, to get you to understand how treacherous is this idea that nearby solutions in a tube will go up a nice tube like that and come back down. Yes, but that tube isn't what you thought it was. It's more like that 4-circle paradox. So it's more difficult than it seems. Now, how do I do an nth order equation? It's easy. In principle, I can reduce them all to first order equations. I have 28 first order equations. I predict each variable. I evaluate each derivative, I get a new slope, I make a corrector prediction of each one of the variables, and if all the predictors and correctors are close, I take the step. Otherwise, I've got to shorten up the step size and do it again. Or alternatively, repeat the corrector a couple of times. But it's probably not good to repeat the corrector too many times. It's probably better to shorten the step size. So you see, I have a problem which in high dimensions is rather troublesome. It isn't what you're likely to think it is, because that four-circle problem plus other things I told you about n-dimensional space tell you that things are not nice. They are much more difficult to grasp. Now, I said to you when I took up digital filters, I had studied these things, and in the predictor corrector, the corrector particularly, yn plus 1, the new point is a0 yn plus a1 yn minus 1 plus a2 yn minus 2 plus h b minus 1 yn plus 1 prime plus b0 yn prime. Now, it looks like a difference equation, but this y is going through a differential equation and coming in there non-linearly. So there's not only feedback from the y's back this way, going around a little loop like this, there's also this going through the derivatives through a nonlinear transformation and coming back to affect the y. Therefore, the problem of the feedback stability of a differential equation, while resembling that of a feedback, of a infinite impulse response digital filter, has this extra complication. In the other one, these were the input signals. Now they are a consequence of this, and there's more instability. And so you'll have a little bit more trouble. But there's a different thing which I want to bring out to you. When I talked a few moments ago, I said I fit polynomials. What was I fitting in the filter theory? I was fitting frequencies, right? Now let's consider the difference. I am building a simulator to simulate landing on Mars. If I use the polynomial approach, what I will get for a trajectory is one, I'm exaggerating, there will be corners in the acceleration, because the polynomial here doesn't fit the next polynomial. If I do the frequency, I'll get the frequencies right, but I won't get the position necessarily as well. Here I get the position right, but the feel is wrong. Here I get the feel right, but the position is likely to be wrong. Now you can also see that if I have a little wiggle like this, it's going to feel different than this guy. A high frequency wiggle is going to be serious. This one will ignore it, because they're using a low sampling rate. You won't see it. It'll be aliased down to a low frequency. So we ask ourselves the question, when we design this simulator, what do we want? Do we want the solution to be accurate, or do we want it to feel right? If I were exactly right, the two will be the same. But if there's going to be an approximation, one of them will have little corners in the acceleration, but the other one won't be quite as accurate in landing. But the guy's got a joystick there to steer by. He can make small corrections as he's landing. So if I don't calculate the position quite as accurately, the pilot anyway is going to do some self-control to get land where he wants and not on top of a rock. I'm inclined to believe that I want to give that man or woman the feeling as they're landing that they've had the same experience. Now, I can't fake it out completely. I can't fake out for very long the lower gravity of Mars. Not for very long can I fake it out. So I can't produce a perfect one, but I at least can have it feel right without any jiggles. On the other hand, I don't know where to look for the question. What does the pilot feel, apparently mainly through the seat of his pants, or her pants? Do they feel the Fourier series frequencies, or do they feel the complex Laplace transform frequencies? Which ones must I get right, and what range of values does the pilot actually sense, and which ones can I ignore? We don't know as much about that as we should know. And therefore, we really don't know how to design simulators. Particularly in one landing on Mars, it's going to be rather unpleasant. It's one thing to go for the moon and fiddle around for a week. It's something else in a capsule to go a good part of a year coasting, and then land and spend a good length of time there, and then another good piece of a year to get back. It's a rather different thing all the way around, as you well know. So it's a problem which has not been answered. I'm not prepared to give you. I have favored the frequency approach. I have favored the frequency approach because it tells me more about the physics usually. Except for falling gravity, I have looked for 50 years for a physical effect which is polynomial. Falling body in a uniform gravitational field, yes, but nothing else. Exponential frequency frequently tells you a great deal about stability, if you're worried about that, like with stability theory. It tells you a lot of other things. When I told you how I solved one for a sampling rate, I got the frequency response from them up to 10 cycles. Above that, they'd worry about, below I had to. I connect what I see. And if I have to take small step size in a piece of thing, I can tell the guy, you know, there's high frequency stuff there. That is meaningful to a physicist. To tell them, well, you know, it doesn't look locally like a polynomial, doesn't help out much. So I tend to favor the frequency approach over the polynomial approach, but they're pretty much the same. It's a question how these coefficients, A0, A1, A2, and B minus 1, B0, B1, B2, how they are picked. You pick them one way for polynomials, you pick them another way for frequency. And what frequencies you want determine what the coefficients will be. But the arithmetic computation is basically the same, except that maybe one time or two you may get a zero coefficient which saves a multiplication. But as I say, you can't make a living out of saving nanoseconds these days. One operation is a nanosecond. You can't make a living at that. It's not worth it. So you have to do something else. Now I want to tell you another story. In the early days of Nike, we were firing what amounts to a telegraph pole, we called it. We fired a missile like that. We wanted to go through a certain range, and somewheres out there we would blow it up so none of the parts could fall out of the range. And if the thing got out of the way a little bit, the control brought it back in on the trajectory, because we wanted to get that trajectory. We wanted to spend some time here, some time that altitude, so on, so we could get the drag coefficients of real atmosphere and the real equipment, and with varying velocity. So going up we had one velocity, another when you come down. We were trying to gather data. We had a half a dozen flights, something like that, planned in order to get the data to go on to the next stage of refinement of design. Well, I never went to field tests. I didn't want to go to White Sands, which was full of scorpions of sand, and I don't believe in going to field trials anyway because they're always confusing. Well, my friend comes back, and he's wandering around the hall, and I say, what's wrong? He says, the first two of these blew up in midair. They shook themselves apart, the parts fell out of the sky. The telemetry doesn't tell us what happened. We don't dare to fire the next four because they'll shake themselves apart. But if we don't, the project is stopped for lack of data. I say to him, Don, give me the equations, and I will put a girl on a desk calculator in those days, calculating what the trajectory is, and I'll tell you what happened. They, in a week, delivered the equations. I put a nice lady on the job. I have a little trouble with her keeping her on the job because she thinks she's losing information she isn't, because she doesn't understand what she's really doing. And we calculate. And what we find out is gorgeous. You know pitch and yaw. For time, pitch goes like this, and it settles down, and pretty soon it's found to go wiggle again and settles down. Yaw was found to go so the energy in pitch threw it into yaw, the energy in yaw threw it back into pitch. And these waves got bigger. When I showed it on a Tuesday morning out of Whippany to a bunch of people, I just showed these sketches, one in black and one in red, one's pitch and one's yaw. They knew immediately what was wrong. They had forgotten the crosstalk. In fact, one guy got up, stood up, hit his head against the wall in anger, how stupid he was. Now, what did I do? I did very little. I only identified, having come from Los Alamos, that I could calculate what happened in a disaster if they gave me the right equations. And then I put a girl to do the work. I didn't do anything, she did it. What came out was that from peak to peak here was about what the telemetry did. When the telemetry got very bad in this one, when it got very bad there, that period was about right. Furthermore, the shake was right. The whole thing was right. Why was it right? Because they gave me the right equations. It wasn't the computation. It was that they modeled the thing correctly. And we simply simulated. Now that is now much more common. But now let me tell you what really happened. When we get everything ready, I say to them, well, it's the seventh order system you gave me. You've got to give me 7 initial conditions. What altitude, what angle, what's this, what's that, what are all the 7 variables doing? I haven't got the manpower in those days to calculate from here all the way along. I have to start somewhere as near the disaster. After all, it took the girl a week and something to do the calculation. I can't afford to go much. So we have to guess. But you remember, I knew that this was a telephone 1. If they were a little bit wrong, the guidance system would bring them right back on the path. Errors here in initial conditions would be wiped out because of the nature of the problem. There was a convergent direction field behind the problem. Therefore, I could do it. Example of garbage in, good answer out. It's easily done. That's a good case. Let's see. Let's take another one. Now there's another one like that. When I was at Los Alamos, I discovered we were drawing on a big piece of graph paper an equation of state with big French curves, a great big piece of paper. We read the thing to 3½ figures, meaning we guessed at a 5 or a 0 for the next digit. We took those numbers to 3½ figures, subtabulated to 5, and sometimes 6. Those were the numbers we used for the problem. Now, I knew the original numbers were not very good. They were based on high pressure measurements in the lab, which were not very high in view of the pressures of the bomb. There were some estimates of what pressures would rise in earthquakes. There were some estimates of pressures in the centers of the sun, and there was, at the very far end, was some estimates of condensed matter completely, a Fermi theory coming off. From those scattered points, we drew a curve. It looked plausible. But the curve could not have been good to 3½ figures. It was probably good to about 1½. Yet, to my surprise, our calculations agreed very well with what measurement we made after the shot, the Trinity shot down in Alamogordo. I deliberately stayed an extra 6 months. I asked Bell Labs for permission to stay another 6 months. Partly it was to try and find that out. Well, I believe I told you why in an earlier lecture. When the shell went up the curve, it came back down. What I was actually using was the second differences. I was really using in the computation the curvature. But since the points were nearby, I had to have a lot of accuracy to get a reasonable estimate of the curvature. And since the shell went up the curve, it was the average curvature that I had to worry about. If I got too much here, there would have to be some out there to compensate. And furthermore, some occasionally got pushed a little way back before they completely melted. So again, there was a place where inaccurate numbers were going in, but the way they were computed with, they did not affect the accuracy of the answer. Now, I want to remind you of H.S. Black's great idea. You have a signal and you have an amplifier, 10 to the 8th, we'll say, minus 10 to the 8th. This is Y and this is X. We'll say that's 10 ohm. The input is now Y plus or minus 1/10 x. Multiply by 10 to the 8th with the sign change, and that's going to be the y. When you solve it, you'll find that x is roughly 10y over 1 plus 10 to minus 7, or 10 to plus 7, 10 to minus 7, something like that. What counts is if that resistor is accurate. This is 10. If it is, the amplifier has got some aging and so on, it drifts a little bit, that's the term that changes. The answer is still very accurate. By feedback, which H.S. Black, Harold Black, doped out one day crossing the ferry on the Hudson River getting over from New Jersey to New York, he realized that that's what makes things work. You inherited the thing, but it was done by people I knew. Now this impacts good design, but it's not been worked in design theory as far as I know. It's evident if you can get this kind of negative feedback. You can design with basically inaccurate components and get accurate answers. The same as I told you, error correcting codes. I can build a system with inaccurate components and get fabulously good results out. These principles need to be more incorporated into design than they are now. They're sort of grafted on the end rather than understanding directly what is going on. Now I want to look at another problem, which is, it's a good story. I come out looking good, but not along the way. The guys in transistors wanted the following equation. The hyperbolic sinh of y minus kx, y of 0 equals 0, y of infinity is asymptotic to log 2kx, which you can see comes about if I simply put y second equals 0. And 1/10 less than equal to k less than equal to 10 for varying values. And it's the big k's that gave me trouble. Well, the solution looks more or less like that. It's got the right asymptote. It starts out here. Well, I'm not bad at this. I was a mathematician. I can get power series solutions here, but the power series solution didn't converge very far. Well, I can do better. I got expansions and arctangents and other things, but they didn't get very far. They didn't get anywhere here. They were limping around in here. Well, it was a very interesting problem. I got half the math department probably trying to calculate some way or other what on earth was going on. So I went to the proposer and said, wait a minute. This condition in infinity, infinity doesn't exist, cut it out. And he said, well, in those days, transistors being what they were, he said, that's the number of layers of atoms. And the transistor we're building, it might as well be infinity. I had to agree. When you get up to 10,000 or something, it might as well be infinity. Secondly, I objected to the equation. There must be something wrong with this equation. Because let's look at what happens. If out here I get a little bit above y, the sinh y is very large, the curvature is positive. If the y is a little less than it should be, in the past, when I had a divergent direction field, I had learned you just integrate the opposite way. But here, whether I go this way or come back this way, it's like I'm walking on the crest of a sand dune. If both feet get on one side, what am I going to do? Now, I have maintained that computing can help in any situation. I can't get the equations changed. I can't get the problem changed. I got to deliver some answers. Or eat crow. I'm not about to do that. I'm not about to say, well, you produce the equation I can't solve. No way. It takes me quite a few days until I realize this very instability is the essence of the problem. Now, I happen to have an analog differentializer at that time, but it could have worked on digital just as well. What I did was I searched for places here where I thought the solution was nearby. I tried various angles. If I picked too big an angle, went like that, a little less angle would go like that, and somewhere in between would go like that and then scoot up. Well, there I have a piece of the solution. Now I start here. And I could get piece by piece by piece that part which either rushed up or down, which must have been a solution. I use the instability to get the answer, right? I came out smelling like roses, but for quite a few days I was very unhappy. Well, I commend to you that just because the problem looks like it can't be done, don't give up. Think about it when you go to bed nights, think about it when you're walking, when you're doing else, and see why you cannot find an answer. And here, unstable, no matter how you look at it, I got an answer. These problems can be done, and don't tell me you can't do these kind of things. It was an important problem in design of transistors at that time, and I felt that as a Bell Lab employee who was working on transistors, I had to help them get from the original design of the first transistors to reasonable production of manufactured ones, and it took about 10 years to do the job. So off and on for 10 years I did computations for them like this. And this is one of the better ones. Let me go on now and talk about a Rorschach test. In my youth, they were very common. What you do is you take a piece of paper, put a drop of blood, ink, and you fold it. When you open it up, there's a symmetric pattern, a random one. What you did is you took a bunch of these blots, you showed them to the patient or the victim, whatever you want, and asked them, what does it look like? It's like looking at the clouds and saying, oh, that looks like a sheep, or oh, that's like a camel. You're putting it in. The shape is what it is up in the sky, the same way. And there's a famous one about where a guy was testing a little boy, and the guy said, oh, that looks like my mother going to bed with my father or my uncle, and that looks like this one. Awful. The psychologist finally said, you know, the kid, you got an awful dirty mind. He says, no, you got a bunch of dirty pictures. The Rorschach test was supposed to reveal you because there was nothing else there. You were interpreting things. There was nothing there that was random. Well, I believe they've given it up now because they recognize it isn't really too good. But it was used for quite a long while. Now, you know what a Rorschach test is. Let me go on. We had a psychologist for a while, and I got to be a friend of his because he had quarreled with his boss over in psychology, and they moved to the math department on the grounds the math department could tolerate anything. And my boss said, you know, Alex babbles over that hall. It's going to be kind of lonely with nobody to talk to. I think, Hammond, you better go by and talk to him periodically to see if you can't keep him cheered up so we can keep him. He's a good man. So I got involved with Alex because I was told you've got to keep the guy happy. Well, he told me about an experiment he had done. He built a box, a red light, a green light, and something like 12 switches. You set the switches one way, you push the button, and either the red or green light came on. You got 20 tries, whereupon you wrote your theory of how to get the green light to come on. That theory was passed on to the next victim. That victim got 20 tries. That victim wrote their method of getting green light to come on, and so it went. And the ostensible purpose of the experiment was to show how theories gradually evolved from data. Well, Alex remarks to me one day casually, of course, the green and red lights were connected to a random source. And he says, none of them ever spotted it. With no hesitation, I said, huh, not one of them was a statistician or an information theorist. That takes a little checking. I was right. They were at that time the only people who were ever taught to replace a theory by no theory. You were lovingly taught in your physics and engineering how this theory is replaced by that theory. But replacing a theory with saying, that theory is wrong and I've got nothing to offer, you were never really taught. It's a very great fault in your education. But that's what statisticians do. The statisticians have tests which say, if it were random, what would I see? Is this significantly different from random? If it isn't, forget it. Now, they unfortunately cannot give exact tests. They give something 90% reliability, which means that 9 out of 10 times you'll be right, but the 10th time you'll be wrong. And you'll be wrong either that you thought there was something where it wasn't, or you didn't think there was something when there was. Type 1 and type 2 errors. Provided all the rest of the assumptions were correct. If everything else is correct, then they will give you 1 chance in 10 of being wrong, or if you want to do a lot more experiments, 95% confidence. And it's hard to go from 90 to 95%. You have not been trained at all to recognize no signal. It's just plain noise. But it's very important. And it's a very, very sensitive thing. We have a large number of ecologists out there who are finding patterns and interpreting them as meaningful. A fair portion of those are not. They're finding what they want to find. Now, let me go ahead. I will give you one about simulation of business. J. Forrester, the man who got the patent on core memories and made a fortune out of it, he had been an electrical engineer and he got interested in business. And so he became a professor of business engineering. He tried to apply the techniques that he'd learned in electrical engineering to business. And so he lectured, he wrote a book finally, and I quote from you carefully several sentences. From the behavior of the system, doubts will arise and will call for a review of the original assumptions. From the process of working back and forth between assumptions about the parts and the observed behavior of the whole, we improved our understanding of the structure and the dynamics of the system. This book is a result of several cycles of re-examination and revision by the author. Was it a Rorschach test? Did he find what he wanted to? Did he fix the coefficient until he got what he wanted? Well, J. Forrester is a good man. He probably did not. But in the hands of a less capable person, they're almost bound to find what they want to find. Now, you think you can resist it. Let me remind you the doctors. The doctors wanted to find out whether something were effective or not, so they took 20 people and divided them into 10 who got the treatment and 10 who didn't. Well, if the people knew who got the treatment and who didn't, the people who thought they got the treatment got better and those who didn't, didn't. So the doctors began to realize they couldn't tell the patient. Then they found out that if the doctor knew who got the treatment and who didn't, the doctor saw the patients getting better. So they were driven to what is called a double-blind experiment. Neither they nor the patients know who got the treatment until the whole thing is done, all the data is gathered, then the statistician opens the safe, pulls out the data, and tells you who got the treatment and who didn't. Now, they were driven to a double blind because they found themselves, with the best intentions in the world, could not avoid seeing what they wanted to see. Now, let me warn you about that. The double blind experiment is supposed to work, but let's not kid yourself. Nowadays, with modern computers particularly, a group of patients who are going to be treated on something, new experiment one of my friends is in one of these treatments, they get a bulletin board. So there are 20 people there, and 10 of them are going to get placebos and 10 are not. And on the bulletin board comes 10 guys who said, gee, I got a headache and diarrhea, and the other 10 didn't. Who got the treatment? They probably found out, right? Before the docs did. It's very, very difficult to do these experiments. It's very, very difficult not to find what you want to find. It's a very, very hard problem. And it's one you must grapple with. Now, I suggest to you that many experiments are, in fact, Rorschach tests. The guy fiddles around and gets the answer he wants. Certainly, the Club of Rome was that way. They fiddled around with the equation. They got the equation which produced disaster, which they wanted to produce. And I'm afraid a large number of other things that way. And there are some lectures going on which will, in fact, treat the question of how good is data. And as you gather various kinds of data, you get various kinds of answers. Lecture on each topic. In fact, I might as well tell you now, since I've got a little time. The situation is this. I will go through the sequence of lectures as they are, and there's 30 in the notebook, and there's 31 lectures I'm going to be able to give. The Thursday and Friday of the last of the term, I have agreed to give a talk in Los Alamos on the future of physics. And so I can't be in two places at once, and so I could not meet those two. So the last lecture on Tuesday will be the 30th lecture. And I will interpolate one on how do we know what we know, unless some of you come up with, I'd like to hear talk about such and such. Other than that, I'm going to go straight through these things, and I'm going to dwell more and more on this subject. How good is data? It isn't anywhere near good as you wish it were. We constantly see our own footprints when we do things. We do not see nature the way we wished. And in terms of digital filters, we always look through some window at reality. We don't see reality. But it's a window not only of signals, electrical voltages and so on, but it is also very much a mental window. You have preconceived notions and you see what you expect to see. You do not see what you don't want to see. The history of experimental physics is filled with cases where Professor so-and-so finally found this new effect. 20 years before, somebody did a similar experiment, but he didn't notice the effect. He glossed over it and ignored it. Thought it was bad data or something. His records from his notebook show that he actually saw the effect, but he ignored it. The later professor saw it, recognized it, and saw it was something important. It's a very, very difficult business. It's the reason why I'm trying to teach this course. How do you recognize when there's an opportunity for something and when do you not look? Most new ideas are not good. But there are good new ideas. Life is progressing, and as far as I can see, change is going to be more rapid in the future in almost all directions than it was during my lifetime. You are born into an age of change. Accepted theories one day are not appropriate the next day, because the world has changed. I told you several stories about me being wrong on this point, failing to recognize the fast Fourier transform, that I now had a better computer and could calculate what I could not calculate the previous year. I failed to recognize progress. It's a very, very common thing, and this business of making measurements, and the one I commend you particularly, this lovely one my friend Bablis did. The light was actually connected to a random number generator, and these people made 20 tries, reported how to do it. They read the theory, wrote the new theory and so on. Not one of them said, there's nothing there. It's just random. They all found meaning. Now you do this yourself in your life. Frequently you find meaning in events which are probably meaningless. There are all kinds of superstition, like bad luck occurs in 3 runs of 3 and something else like that. There are all kinds of things which you see patterns which are probably not there. I can't say they're not there, but they're probably not. It's very, very hard to be objective. You must doubt yourself a great deal and search positively. Am I finding what I want? You need to lean over backwards and be very careful. Almost everybody will find what they want to find, and that's why we're having trouble now. So long as we search for big effects, that can't be disguised. But when the effects are smaller, then this habit, this Rorschach test business of life, you see the pattern you want to see, and you report that there's a goat in the sky up there in that cloud, and yes, it's a goat. You saw it. It wasn't, but you saw it. You convinced yourself it was there. I have seen it continually, and I've spent a great deal of my life trying to combat the desire to find out what you did was what you wanted. You saw what you wanted to see, not what should be. This applies not only to the technical world, it applies to your private life as well. If you begin to think your spouse is telling fibs, you'll find the spouse is telling fibs. Not the spouse need to be, but you'll see. On the other hand, if you think your spouse is perfectly honest, you won't think they're lying. You won't notice them. You will interpret events whichever way you want to interpret them, and you will project on the other person, not the other person's behavior so much, but how you would have behaved in the position you think they're in. You project your feelings. For example, my brother, who told me one time when we were still in our teens, he said, everybody in the world's a liar. I said to myself, being a young kid, I'm not going to argue with my bigger brother. How can everybody be a liar? It's defeating the word lying and honesty. I thought for a while longer. I said, no. What he is saying is that he, in the positions he projected other people, would have told lies. He cannot know that everybody's lying. He projected himself into there and said it. Because at that time, he thought people lied. He did a fair amount of lying. You do this a lot. So it's not only your private life and your public life, it's the whole thing. The whole organization you're in has the same trouble. When they search for discrimination, they find it. When they search for that, they find it. Is it there? Who knows? It's not obvious. And this is the world you're coming into, and this is why I want to talk about this thing. Good data in, bad out. Does that give you some examples? Bad data in, good answers out. Any number of things. It depends upon this feedback business. And I have, after many, many years of meditating on network, which are the flow diagram of the control and of a program or a patch board on a differential analyzer, whether the net amount of feedback is positive, so it's unstable, or negative, so it's stable. Because generally speaking, there's some positive feedback here, some negative feedback there, and so and so. Which dominates? I could never give you a decent answer. I never learned to do it. I did only try to instinctively search how much gain is here. So long as it's negative feedback, you've got great stability. But if this is positive feedback, it's going to rush off to one extreme or the other. But of course, that's feeding into other circuits, which have negative feedback, and they're producing more stability. How the whole balance is extremely, extremely hard to find out. But that's what makes the difference in simulation. If there's enough negative feedback, I can get very good answers, even from bum data. If there's a lot of positive feedback, I can't get very good answers at all. And this, I still feel this example I drew it here to erase the e to the minus x squared is such a perfect example. It shows you within one very simple problem how I can get from here to there accurately, but I can't get the halfway point. I can get the whole computation right, but in the middle it isn't accurate. Because there was divergence here and enough convergence to compensate here, I come out fine. That's the way the problem is. That's the problem you face on all simulations. And since the people working for you doing simulations are not going to be as sophisticated as I hope you are from having heard these lectures, you're going to have to keep an eye on them, that they are not feeding you that which they and you wanted to hear. Particularly junior officers are very sensitive to senior officers' desires, and they know how to feed the senior officer what they want. So the senior officer gets what he wants, according to what he wanted, but not what he really wanted, which was the truth. So I leave you the problem. I'll see you tomorrow. And we'll start on optical fibers.